It stopped. Good catch, Josh. I did hit it before, but probably in the brouhaha of changing screens and whatnot, it didn't. So thank you, Josh. So when we're talking about reflections, there is a law that is pretty obvious once you do the experiment. What does that say?
The reflections they're like equal
To what?
to like the one going in, the one coming out.
Mm-hmm.
So the angles of incidence and reflection are equivalent in measure?
There you go. There you go. That's even using the right terms. The angle of reflection equals the angle of incidence. Using the terms. So I'll sketch that out right here. We're going to put a mirror right there. And I'm going to show that that's a mirror by making sure that behind it looks opaque. So I just put a little hatching back there. And then just to avoid confusion, let's just label this as mirror. So we've got a light ray coming in. I'm going to have it coming in from the bottom, striking this mirror. This will be our incident ray, so I'll put a little arrow going to the right. And we often represent light, at least in this geometric optics unit, as light rays. It travels really as a wave, and we'll talk a little bit about that by the end of this chapter. But for all the purposes that we've got here, rays are going to help us a lot, visualize this a lot more. So there's our incident ray, and the way that we measure rays always goes back to, let me see if I can't change that. Always goes back to the perpendicular normal line. That is not very good. I'm going to see if I can fix it in a sec. It's not co-op. It is not co-op. Okay. So I'm going to do this. I'm going to try and better to make that actually come straight out, or at least be close. So this is a normal line. And all of our measurements are going to be relative to that. And then the angle of incidence then is right down here. And what the law says is, and this is going to be particularly hard for me to draw out, is that as a ray comes in, it's going to be reflected at the exact same angle measured from the normal, but on the other side of the normal. So I'm going to do my best. It's pretty good. That will be our reflected ray. And this is the angle of reflection. And that's all there really is to the whole mirror thing. Now, the configuration of the mirror can change and complicate that. But the law and the rule that we apply doesn't really get any more challenging. What we're going to be looking at, though, too, is where do images form from this? And so I'm going to put a new little bit here. What we call images occurs when light rays bounce off different parts of a mirror in this case, and then form or intersect at one point. I should say, and when reflected rays. Yeah. Okay, so let's take an example of that. I'm going to again try and sketch that as best I can down here. So we've got, shoot, I screwed up at the last moment. Got our mirror. Did it again. Let's try this. That could work. Ignore that little tail on the end, but it keeps it at a right angle. So here's our mirror. And then I'm going to make what is called an optical axis. Again, don't worry about the tail on the far left. This is important though, because we'll use it as our measurement point for a lot of different parts. And then we're going to have an object. And very often we make an object that is an arrow. I'm going to make that green. I'm going to put an object out here. So we've got this object standing in front of our mirror. We want to find out where is the image for this object going to form. And so we're going to draw several light rays coming from it, and where those light rays intersect, that's where the image forms. So I'm going to do a couple different ones using the law of reflection here. One of them is, let's make this one orange. First one I'm going to draw is going from the top of it, of the object, to the where the mirror intersects the optical axis. Okay, and that's going to hit with some incident angle, which we often abbreviate as theta I. Let's go up and add that to our first drawing up there. Theta I will be our incident angle. Theta R then will be our reflected angle. How is this going to reflect then? Well, same angle, but on the other side of the normal, which is our optical axis. So I will, ignore that first one. I will do my best to draw it down here and keep it at the same angle. Now, if I had a protractor like you will in the homework, I would just measure that angle, make sure I get it at the same angle down, and then extend it that way. Okay, so there is ray number one. Now I could draw any other rays from this and just see where these reflect. So I'm going to do a couple different ones. I'm going to do one pretty easy one, going straight to from the top of my object to the mirror. Okay, so let's imagine that that is perfectly parallel to the optical axis. How is that going to reflect?
Wouldn't it go back where it came from?
straight back where it came from. Is if I got it perfectly going in there, yes, it would go straight. Oops, I gotta get to the angle. It would go straight back. Huh. What do you note about, let's call this, orange one is going to be ray 1. Shoot. Red one is going to be ray 2. What do you notice about ray 1 and ray 2? Where are they going to intersect? They don't. Crud. Okay, let's try another one. Let's try this one. I'll do as black. Blue, I guess. Let's draw another ray to the mirror. I'm going to do this one a little shallower than my first. Okay, so it's going to hit there. It's going to, if we would draw a normal line coming straight out from the mirror, it would reflect from that point at the same angle, but downwards. Oh no. That one doesn't actually hit either. So we have a problem here. These aren't going to match, aren't going to meet in space. Can I do anything? No. I'll try and freehand it. So what that means is that this mirror is not going to form an image in real space. But if we take each of the reflected rays and extend them back, and I'm going to try and freehand this because I don't know of any good way to make a dashed line. Usually we would make these dashed when we're going behind the mirror. So I'm going to take my ray 1 and I'm going to just try and draw a straight dashed line backwards. These are called imaginary rays. And imaginary space back here. It's imaginary because the light rays can't actually get back there. This mirror is opaque. It does not allow light rays to pass through it. But our eyes are really cool. And I'm going to now extend R2 straight back as best I can. Again, if you're using a ruler, this is way easier. And then I'm going to do the same thing with my reflected ray of ray 3, the blue one. And that defines where an image is formed. So back here, this is where the tip of our image is. And then if we followed down and took different slices of this image, we would find a similar thing, just straight line approaching the optical axis. There is our image. So importantly, the image from this mirror, and in fact, all plane mirrors, plane meaning flat, not ordinary. This is called an imaginary. No, not imaginary, a virtual. Got my terminology mixed up there. Virtual image. I want to go up and change that to my orange writing up here, not imaginary space, virtual space. My apologies. So what a virtual image means is it can't be projected onto something. But it can be formed when a lens is used. And lenses are our next topic. And so what this means is that although there's no real image, the light rays never do connect with one another and intersect in real space. The magic of the lens in our eye allows us to perceive the image behind it. I didn't do a very good job measurement-wise here. You'll see this better in the homework, but there is a relationship between the distance from the mirror to the object and the mirror to the image with all of these as well, and that'll become more apparent with careful measurement, and we'll talk about that again in the future. If light rays do actually, if reflected light rays do actually meet, we call it a real image. This is one that can be projected onto a surface. Okay, and that would have come about if R1, R2, and R3 had met someplace over on the left where the light rays actually travel in space. They didn't, but they could be extended behind. And so what we're going to be exploring this week then is what's happening to those light rays as they bounce off mirrors or as the virtual rays extend beyond the mirrors to see where images are formed and be able to make different measurements with the images. I want to see very quickly before I let you go if there's anything else I need to touch on. So the next couple of, well, tomorrow we're going to meet again to discuss the reading. So make sure you have submitted your reading before then, and we'll have, in all likelihood, some more time to go over a few questions. And then we have a couple days for work time on homework 11.1, which means during class time or outside of class time, work on it, finish it up. If you have questions, I'll just be hanging out during class time in this meeting. And if you come up on my list, I'll be able to let you in and you can ask questions during that time for clarity. For the first homework, you're tracing some rays as objects emit light onto mirrors and seeing where the images form. So it's more a practice of this law of reflection and see what happens with it. We're going to expand beyond that into some differently shaped mirrors. And in your kits, I wanted to verify something I think I remember, but it's been over a month now since I built these kits. You should have, with the mirror like this that you did or are doing the experiment with, and note that this is a flexible mirror. So you can bend it a little. You can also snap it. Please don't snap it. I'm not sending you a new one. But you can flex it, and that will be important for our next lab. But correct me if I'm wrong, but I don't think I had enough mirrors, curved mirrors, for you to see, like this one that is actually domed, right? You don't have these in your kits. Okay. You should have two lenses that are domed like this, one concave so it's inward and one outward, but not mirrors. So when we get to that part, we'll be able to do a quick exploration with this flexible mirror, but then we'll have to do more talking and classwork with the curved mirrors than we would do ideally. Okay. Okay, so do the reading. We'll meet back here tomorrow. As usual, you can send me emails with questions, that sort of thing. And if necessary, we could even meet like this if you wanted to at some point like that. Okay? Okay, have a good one. This will be posted shortly in case you wanted to go over anything. See you tomorrow.